Hi, welcome back to 1-Bit Fever Dreams. This is the long-awaited third video on my series on Think C Mac programming. Today we're gonna learn about a big problem that awaits every programmer that wants to do a fast animated game or just fast animation in general, which is flickering and screen tearing. We're gonna learn exactly why the problem occurs and what you can do even though you have limited CPU resources available at your disposal. So stay tuned and let's figure this out, and it'll even overflow into another video where we're gonna do exact time measurements and we're gonna prepare our stuff without aiming in the dark. So let's check that out.
If you prefer following a sequence from the beginning, head over to the description and find the previous 2 videos of the series. Last time we had a game, allegedly, that had keyboard stroke movement and incredibly primitive graphics. We created a simple loop that went over keyboard detection, data updating under certain conditions, aka the logic part of a loop, and then straight to graphics directly on the screen. We totally disregarded what happens in the hardware when we did our graphics. We just did it as fast as possible. And the price to pay for that was a very classic case of flickering. Today, we will pay attention to how graphics work and will obey the rules of the hardware screen as we're being chased by the electron beam. We'll be disciplined in exactly when we should draw. This will solve our problem. The topic in this video is an essential part of your Macintosh game programming for anything that involves real-time action. I'll show you how the Think reference documentation suggests how you should solve that problem, but this might feel like an unsatisfying solution out of a magic hat. In order to appreciate what is going on, I'll have to dig deeper and explain more concepts related to exact timings, and this will actually overflow into the next video of the series. Now that the plan is decided, let's check out how the video display works on a Macintosh. I'm gonna crack open my hardcover edition of Inside Macintosh, volumes 1, 2, and 3 bound together. So in volume 2, you'll find a section on the vertical retrace manager, which is where you learn how to deal with the vertical blanking interrupt, which is a thing we'll use extensively. And in volume 3, there's a section on the video interface. It'll tell you all about the sections of the screens as they are being drawn onto, with the timings in microseconds down to what happens on every line. Very descriptive stuff. Simply put, flickering occurs because every graphic operation you do takes a certain amount of time. It doesn't matter if it's optimized or not, because nothing can be instantaneous. Whatever you decide to do with your drawing lines of code, the screen will refresh the graphics on the whole screen every 16.6 milliseconds. During every screen refresh, the ones and zeros in the content of the video memory area will shape how the electron beam sweeping across the screen is acting to produce a video image. If your code is being too slow or it's happening at a bad time, or both, you risk having a part of the graphic representing the old state and another part representing the new state simultaneously. This is often known as the tearing effect. If you're whitening out the old graphic to erase the old position and blackening the pixels for the new state of the image, this will often cause what is known as a flickering effect. This was our problem in the last video. The strategy to avoid this is simple in theory, but can be hard to achieve in practice if you're just guesstimating things. According to my Inside Macintosh book seen a minute ago, this is how a full screen refresh is set up in order to draw all 342 lines of viewable graphics of 512 pixels each. Assuming you start at 0 second in the bottom right corner right after the last pixel has been drawn, the monitor starts to generate a vertical blanking refresh interrupt. The beam will take a small but still significant amount of time to go all the way back at the top left to get ready to draw the first line. Each line starts with a left side black border followed by the active 512 pixels and finally a right side black border and takes exactly 32.68 microseconds each. A horizontal sync signal starts after the rightmost pixel of the line. To my knowledge, there is no way to exploit that signal with an interrupt on the Macintosh, but it would be hard to make it work because the time it takes for the beam to go from the end of a line to the start of the next one is a mere 12.25 microseconds. I realize it's harder to think in terms of microseconds, and it won't exactly be necessary for programming. The only idle time we can sync to is at the vertical blanking interval. It's the longest one, and we can actually exploit it for our goals. The idle time we can harvest between the last bottom right pixel and the first top left pixel is equivalent to a whopping 28 full lines of delay, or if you will, slightly above 14,000 pixels. It can seem like a lot, but it's just about 1.26 milliseconds. 16.6 millisecond per frame being the time period, you get the screen refresh frequency by getting the inverse of that, which gives us a familiar 60.15 Hz for the compact Mac screen. This feels familiar to gamers as it's a well sought after minimum standard for fluid graphics, even today. So what is the payoff for knowing all of this? If you can make your code act at the start of the VBL and do all your graphics during that 7.5% of idle time, you will never get flickering nor tearing. If your graphic has to happen at the very top left, well, my friend, you're playing with fire, and you're giving yourself the smallest delay possible, and the electron beam of death will catch you red-handed. If you instead draw in the bottom right of the screen, that's much safer, since you're exploiting the VBL delay of 1.26 milliseconds, plus almost all of the active full screen, which is shy of roughly 15.3 milliseconds. That brings us close to a total of 16.5 milliseconds of safe buffer. We should definitely see a difference between attempting complex graphics in the top of the screen versus the bottom. Let's exploit the VBL, but how? Tactic number 1 is to wait for the VBL and draw ahead of the beam. This is not recommended unless your graphics are really simple. It will not work with full screen graphics because you only have 1.26 milliseconds to do everything before the beam starts at the top left and might get in your face. You can attempt to optimize things by only drawing what needs to be changed, but it will still probably be a tight fit. Only experts or heavy tinkerers can navigate here. The result will be a crisp 60 FPS if you can pull it off. Tactic number 2 is to wait for the interrupt and draw after the beam has just passed you. Indeed, if you do some housekeeping tasks during the 1.26 milliseconds of the VBL, such as getting information from the keyboard and mouse, and possibly calculate some game logic, you can get away with it. You will let the beam get ahead of you and draw on the same frame, assuming you're concentrating on the top left first. Make sure you're not faster than the beam before you're done and do it all over again in the next frame. The result will again be a crisp 60 FPS with a 1 frame lag, which is hard to notice. Tactic number 3 is to once again wait for the interrupt, but give yourself a much more relaxed interval of time to do everything, because you're not going to draw on the screen at all, at least at first. you're going to do it on an off-screen bitmap, a section of RAM that isn't tied to the video section of RAM at all. This is for when tactics number 1 and number 2 did not work out because you had too much to prepare and too much to draw, which takes longer than 15 milliseconds or so. It is not hard to reach or cross that limit, especially if you're after full screen graphics. So, in odd numbered frames, while the beam is busy redrawing a stagnant first frame of video with nothing new in it, you're flipping bits in your off-screen bitmap. Then you're onto even numbered frames, and you can perform tactics 2, which is let the beam get ahead of you and copy over your prepared buffer into video RAM. This way, every odd numbered frame will bring nothing new visually because you're working in the background, and every even numbered frame will bring a whole freshly updated screen all at once. The result will be an acceptable 30 frames per second, good enough for most types of action games. For example, some games are calculation intensive and will sacrifice more frames of drawing in order to make enough time for all of their math, such as Apache Strike seen here. I'm sold. How do I do it? So this is where things were left off last time. This is running on a hardware Mac Plus. So there's movement and there's still the good old flickering. The cheapest way to make sure we do tactic number 1 is with a tight loop. There's an Apple global variable called ticks. That's a 32-bit long and keeps the amount of frames elapsed since the machine was turned on. I'm going to implement tactic number 1 by assuming my main loop is able to do multiple passes every frame. And remember, it checks inputs, draws the graphics, and then verifies the game logic, such as the winning condition, the scorekeeping, and whatnot. First, let's set a global called ticks so far, and set it to 0 long. Then I'm surrounding the deal graphics part of the loop with this conditional. This will ensure it only draws stuff whenever the global ticks has been updated away from my old value. Let's put it on the real hardware. Looks pretty good, right? But wait, it's not all good. So I can move around and whoa! You can see a flickering is coming back here in the top section of the screen. It doesn't affect the bottom because, as I said, the electron beam as a way of catching you unawares when you try to draw at the top of the screen. So let me try to find a better position to illustrate my point. So here, right there, you can see both the whitening of the pixels when I try to erase the rectangle and when I try to draw it back. I'm caught midway between those steps. A lot of steps are needed to do tactic number 1 properly in a game loop situation. None of these were thought of by me, but I just stumbled upon a terrific example in Think Reference Viewer under the keyword vinstall. They provide a full example by going above and beyond. The example sets you up with a proper interrupt scheme, meaning it'll wait for the hardware vertical blank signal and immediately attend to a special function you'll be responsible to prepare. In order for the CPU to know where to look for that function, which is often called interrupt callback function, you'll need to prepare a special structure first, a VBL record, and fill in its details about what address your function is located at, how many VBL signals have to pass by before it's used, that sort of thing. So buckle up and let's put all of these things in and see what are the changes. Again, I'm just improving on the code from the last video, so if it feels strange, pause and go check what that was about, link in description. Step 1, include retrace.h, it's a header from Apple. Step 2, define a structure to hold the info needed by the VBL manager from Apple. Step 3, you can isolate the filling in of the record in a separate function that you could possibly reuse in other projects. Take a note of this line, which directly names your callback function that's going to tell your program what to do once the VBL event happens. This count variable is how many frames have to elapse between each call. Right now, I want to do it every frame, so I'll put 1. If you wanted to implement tactic number 3 discussed before, you'd put 2 and you need to launch 2 separate tasks. But let's stick with the first plan here. Step 4. The main star of the show is this do VBL custom function that does what you need. We can be confident it's going to be fast enough, so our graphics are so simple, but we'll see. Step 5 is to remove this from the game loop because it's going to happen in the VBL function. Step 6 is to install the VBL task right before the start of the loop. And then for good measure, let's make sure that the function definitions are there. One last note, this line is the way to get access to your globals from your application. It's a really quirky step, but it's well documented, so you have to paste this little weirdo. So it fetches the A5 register, which is a pointer that points to your globals. So let's go back to the machine, let's move around. It looks good, but the problem remains at the top of the screen again. There's just too much going on with the erasing and the redrawing of the rectangle. So what can we do? Let's go back to the code. So what if I added this loop to cause a very cheap delay? So while I'm here, I'm going to add the hide cursor function in staging area because Macintosh actually has other tasks to attend to while there's a vertical blanking interrupt time. And in the cleanup area of my code, I'll add the corresponding show cursor once the application is trying to quit. Let's see how things are improved. So it looks good, but there's still a small amount of flickering at the top of the screen. So this technique is quite tricky to get right, but if you limited the movement to the bottom of the screen, there would be no problem. You could also aim to dedicate your drawing at the top of the screen instead of the bottom. So it's not easy to get right. But let's explore a better technique involving an off-screen bitmap. Here's how I would go to implement tactic number 3, which relies on bitmaps. I'll define a flag called even odd that's false during odd frames and even otherwise. Then the graphics themselves will be stored in 3 bitmap objects. I might as well because we're gonna have to think ahead with full bitmap graphics eventually. Let's add some initializations in the staging area. I added a pointer to my main window so I can better target it when drawing to it later. And here I have to massage my bitmap so that they are the right size and some RAM has been allocated to it. Since I need a 16 pixel wide by 32 pixel high player rectangle, I have to set the row bytes to 2. Remember that each byte is 8 bits, and in the 1-bit monochrome world, every individual bit is a pixel. In plain English, a row bytes of 2 will be 2 times 8, so 16 pixels wide. Following those lines, I go over every byte and set them as black using the value FF and X. I could also have set them as 255. The same deal happens with my goal rectangle, but here I'm trying to put it an interesting pattern by writing some bytes. I can't access the same quick draw pattern fill that I did last time. There's a way around this issue, but it's a fight for another day. Last but not least, I'm devoting a full-sized off-screen bitmap which acts as the graphics prep area happening on every odd frames. When we're sure it's finished, it's going to get copied over on every even frame. Hopefully, the electron beam will never meddle in the middle of any of this. So this is my new way to draw the graphics. You can pause the video and check the details on there. Here you can see that my draw player routine has changed quite a bit. I'm using copy bits, which is tailor-made for bitmaps. It's kind of the standard way to copy those bits. There are more efficient ways to do this operation, but we'll look at them in future videos. So we're back on the hardware, and there's no flickering. And you can see the vertical position doesn't affect things anymore. But we sacrificed a bit of snappiness because we're now dealing with 30 FPS. We're drawing every other frame now. Alright, now's a good time to end the video. Hopefully you understand the basis behind flickering and tearing, and you gained a conceptual idea on how to fight against it. As a side bonus, the drawing strategy is going towards bitmaps, and as you can see here, that sets the stage for animated sprites. If you're curious about what I'm showing here, that's from my last video. As always, you made it this far, please do the regular YouTube actions that you know can help out this channel, and I'll see you in the next one.